That's here's various complexity classes that when you're learning theory, you learn. These we teach them. We're supposed to teach them in 2001. We're supposed to teach them in 3101. I think you're even supposed to learn them in the earlier courses. So this concept of a witness is I think it's a good one. It's all right. So the Euclid, he just wanted to prove the existence of God by proving things, and then Hilbert in turn of the century wanted to know whether everything could be computable, and Turing defined things to be computable if there was a Java program or a Turing machine that on every input in a finite amount of time would halt. So here's a computable problem. All right, so let's talk about various problems. So if I gave you a Java program and I gave you an input and I gave you an amount of time, could you tell me whether that Java program on that input halts in that amount of time?
I guess it depends on the program.
No, any program. I give you any program, any input, any time t. So don't overthink this. Don't remember what you learned from that the halting problem is undecidable. Think about it as what you would have known just straight from you.
And I guess, yeah, just run the Java program, see what happens.
Just run the Java program for see what happens. Yeah, run the Java program, in fact, for t time steps and see what happens. Is that a good algorithm? It's a perfectly good algorithm. All right, so that is a computable problem. All right, here's another problem, which I'm telling you, in fact, it says right there, computable. Here's an uncomputable one. I just give you the Java program in the input, and I don't give you the running time, right? Now you want to know, does there exist a running time for which it halts? You see the difference between these? Right? Does it ever halt? Well, here we're given a t, you just run it for t time steps. That's not a big deal. Well, it could be a big t. It could take you a while, but we're not talking about to be computable. All we need is that on every input, you're guaranteed to halt at some point in time, right? And give the right answer. And so if I give you a t, then you're guaranteed to stop in t time steps, right? But if I don't give you the t, then you're kind of looking for a t that has this property. And the problem is, how many t's are there? If t is an integer, there's an infinite number of them, right? And so it's uncomputable, because how do you find that t, right? You can try different t's, and if you find one that works, then great. And if you don't find one that works, then how do you know whether another one would work? All right, so here's another problem that I talked to William about a couple of days ago. I give you just a polynomial over a number of variables. And you could represent it by here's kind of a circuit, but I put the inputs are integers and the gates are times and plus and minus, right? So I give you this and I ask you, and I give you a bunch of integers as input, and I ask you what the output is, right? So is that computable? Yeah, you know how to multiply, you know how to add, that's computable, right? Now, so here is the SAT version, is I give you P is this polynomial and I is this input. and I ask you whether the output's 0, well, you can do that, right? What's the algorithm? You just multiply and sum, you plug them in, and you're good, right? Now here's a version that's uncomputable, all right? I give you the p, but I don't give you the integers, right? And I ask you, does there exist integers for which, if you plug in the integers, you get 0 in your polynomial, right? So that is uncomputable, right? You ask, is p kind of satisfiable? And the reason it's not is because you can try various integers. You can plug in here different integers. And if you find some integers which give you 0, then you can stop and say, yes, look at it, it's satisfiable. But if you don't find integers that work, how do you know there aren't integers out there that do work, right? They could be bigger and bigger and bigger and bigger. And the search space is infinite, all right? So the proof that this is undecidable is kind of a slick proof, and in an hour or two we could cover it, but we're not going to.
Great. Can I ask about that problem in particular? There is a finite set that we could compute for. So how do we talk about, like, the infinite in the case of the infinite set, it's not computable, but in the finite set, wouldn't it be computable? So how do we make that distinction?
But what's finite?
Well, if we take a finite set of integers, say we define a set.
Yeah, exactly. If you gave me if you said, is it satisfiable within a finite set, then you would search that set.
Okay, yeah, I think I think my question's kind of silly now. Okay, thank you.
In fact, it's not. We're going to kind of do your question in about 2 slides. All right. So here, these problems are computable, and these problems are not computable. And where do they actually live? They live over here in a world called acceptable. There's a world in this world. There's a proof, a witness, a proof, a solution that the answer is a yes. And if you give me if your fairy godmother or somebody gives you the witness, here the problem is there exists something, and once you give it to me, I can compute that yes, this is a yes instance because there's something that exists, right? And over here, so here it starts with there exists something that has a computable property. Well, over in the not co-acceptable, the class is for every object, there's something computable is true, right? So those are due, and there's a whole, what they call the polynomial hierarchy, where there exists x for all y's, or there exists x1 for all x2, there exists x3 for all y x3, right? That's called the polynomial hierarchy. Anyway, let's go back down to poly, right? Here's me again, being born and saying, hey, let's talk about polynomial time. That's what I said when I was born. I said, hey, dude, it wasn't my father, it was really me. I said, dude, let's talk about polynomial time. All right, so here's a problem which is computable, and if you want to know the definition of polynomial time, in some ways it really is what can it be done reasonably, right? If you go to any Wolfram, Alfram, and it does it for you, then it can be done in polytime, right? And if it doesn't do it for you, it's probably because it's either in exponential time or uncomputable, right? So here's a polynomial problem, right? In this time I'm giving you an and or not circuit, right? So the difference from our previous problem is that these just like Conrad was saying, he wanted to narrow the set of integers that we consider down to a smaller set. And to really crash his set down, I'm making the integers be 0, 1. All right, it's the same problem, except all my integers here either are 0 or 1, but I have inputs. So and so once they're 0, 1, well, we might as well turn and times and plus into and or, and you get a circuit. And so if I give you the circuit and I give you an assignment, can you tell me whether the output is true or false? Right? Surely you can. You just what's the algorithm? You percolate down the true falses, right? Easy. Now here's a non-polynomial time version. I give you the circuit, but I don't give you the input. And I ask, is there an input that satisfies the circuit? Right? And so is it computable? Yeah, Conrad says it's computable because now we have a finite set of things to search from. And all you have to do is search through them, right? But how big is our search space, right? Our search space, if you have n variables, then it's 2 times 2 times 2. Now there are 2 to the n possible inputs. And so even though it's binary, there's still an exponential number of inputs. So can you solve this problem in exponential time? Absolutely yes. Right? You just try all 2 to the n inputs and you can solve it. But it lives over here in the world called NP versus co-NP. And in the NP world, they're given an instance to your problem C. If the answer is yes, right? Yes, what's the question? Does there exist a witness, a proof, a solution that satisfies our input? If it's a yes instance, there exists something that the fairy godmother could give you so that in poly time you could check it, right? But you'll see if the answer is no, what could she possibly give you to convince you that there wasn't such an input, right? So over here, they're witnesses to prove that the answer is yes. And here they're not witnesses, right? And so those are all our classes, right? Everybody kind of buy that? And in general, I mean, you might say this is sort of who cares, but you go out into the world and ask industry what they want to, what problems they want to solve. And usually it's that they're looking for something, right? They're looking how to build your airplane. They're looking how to schedule your courses. And sometimes there's a polynomial way of finding what they're looking for. Sometimes, more often than not, right? We focus in computer science on these problems. But if you ask for a sort of a random problem that industry actually would like to solve, it's likely living here, that the thing that they're looking for is something that they could write down. So it's only of size n. So the number of them is exponential. And if you gave them one, they would be thrilled because they could check that it works, right? So really, these are the types of problems that industry does want to solve. And often, you know, your boss is going to tell you, and why do you care about this? Right? You care about this is because your boss really is going to, unless, you know, if your boss, unless, you know, she also has taken these various courses, your boss is going to say, hey, I want to solve this problem. And you're going to say, well, no, not only does it feel like it's a problem that lives here and doesn't live here, I can prove to you that it doesn't live here. And how do you prove that? Well, you can't, nobody knows. Maybe the whole thing collapses there like this. But what you are able to prove is if your boss's problem lives down here, then all of this whole thing collapses down, which is not likely, right? Chances are very good that this set and this set are different. In which case you can prove that if I could solve your boss's problem, then I could solve SAT, in which case it all collapses, right? And it's also going to come up in your life where you say, hey, I want to solve a problem up here, right? It's pretty natural. I give you the game of life and you want to know, does this game of life stop? I give you something that, right? I tell you what the weather is today, and I ask, you know, will the weather conditions ever get to the state that it kills humanity, right? If you bound how much time you're studying, then you're likely living here, right? And if you don't bound how much time you're talking about, then you're likely living up here. Either way, you're not living down here, and it's just not going to happen, right? So, you know, people give scientists such a hard time because they don't know what climate change is going to do for us. And that's because at worst, it's an NP problem, right? And likely, you know, if you push it a little bit, it's an uncomputable problem. Not
Sir,
to mention, yeah.
Sorry. Yeah, what do you mean you're bound when you're studying and you're not bound? Like, what do you mean by that?
Oh, if I ask
You said you're bound. Yeah.
Yeah, so let's suppose the weather is, I tell you, and now of course this is a lot of data that we don't have, right? I tell you the exact state of our planet today, right? Suppose you really know everything about our planet today. And I ask you, what will the weather be like in a billionth of a second, right? Newton will tell you how to compute that. And then from that, you can know what the weather will be like in 2 billionths of a second, and 3 and 4 and 5 and 6, right? So you can compute what the weather will be as it moves along, right? So if I asked you, I ask you to tell me what the weather will be like in an amount of time that I can write down on my piece of paper in digits, right? If it only takes me 100 digits to write down the time, then what is the value of the time? It's 2 to the 100 or 10 to the 100, right? Is you following me here, right? And so that's here is that the time, I say, does there exist a time in which the world has bad climate change? And the time is written down within digits, right? Then it lives in exponential time, because 10 to the n, you can run the problem in that much time, right? But if you don't set, if the time could be an arbitrary real number or an arbitrary integer, then it can, right? Then you live up here.
Okay, yeah.
I mean, I mean, we could cover lots of problems that live in these various places, right? And then one of the things that my father's very jealous about is that Steve Cook, who's at just retired from U of T, and I've written a couple papers with him, is he got famous because he proved that if you could solve one of these problems quickly, you could solve them all quickly. And why is that exciting? Is because we probably can't solve any of them quickly, and hence you probably can't solve SAT quickly, and hence you can't solve any of them quickly, right? So this is what Cook did, is he came up with this idea of a reduction. In fact, people were doing reductions before him. I mean, Gödel did reductions. In fact, Gödel sort of talked about these classes too, right? So what question, there's a famous letter that Gödel wrote, which was, so here, this is a logic course, right? So let's go back to logic, right? Let's see here be some logical statement. There exists for all, there exists, right? Some statement that you've all known. And we want to know whether it's true in every universe, right? So we're looking for a proof. So it's true in every, if we can find a proof, then we can check the proof to see if this thing is, right? The proof will verify that the statement is true in every universe, right? But the question is, how big is the proof? If the statement that you're writing, you care about, fits on your piece of paper, and the proof that you care about fits on at least 10 pieces of paper, then you can ask, does there exist a proof that fits on 10 pieces of paper that will prove my statement, right? That all lives in the NP world, right? Because all you have to do is try all pieces of paper. Now, there are an exponential number of proofs that fit on my paper, right? But if the fairy godmother gave me one of them, I could check it, right? Everybody sort of buy that? If I gave you a 10-page proof, you could mechanically check that it proves it, right? But if I don't give you the 10-page proof, how do you find that 10-page proof? You have to search over all possible 10-page proofs, right? Which takes exponential time.
Sir,
Right.
can you also explain CoinP for once? I totally forgot. What's the
Yeah,
difference between NP
yeah.
and CoinP?
All right, let me first compare these again. So if I don't say your proof has to be 10 pages, but, right, I mean, here, let's look at a concrete example. I asked you, is it true that for every values of A, B, and C, and Z, A to the Z plus B to the Z doesn't equal C to the Z for all integers where Z is bigger than 2, right? That's Fermat's last theorem, which people tried to prove for hundreds of years. And it didn't take 10 pages. It took whoever finally proved it, he took hundreds and hundreds of pages to prove it, right? So finding the proof could be really, really hard. And if the proof is arbitrarily large, then it's undecidable whether or not there exists the proof that solves it. Now you're asking about CoNP. CoNP is, there are two ways of thinking about it. Here, an NP problem says, does there exist something? While a CoNP problem says, is something true for every I? Right? Here is it true for one thing? Here it's just, is it true for everything? So that's one flip between them. The other flip between them is here, the fairy godmother could convince you of a yes by giving you the thing. And here the fairy godmother convinces you of a no by giving you the thing. Right? Does that make sense?
Yes, so they are kind of the negation, I should say. No, but they're not kind of negation at the same time. Because
yeah, in fact, if you take this problem and switch true and false, then it comes over here. Right?
Okay.
If I ask you, right, I mean, what do we, in my theory world, I'm always asking you, give me a statement and I want to know if it's satisfiable, right? But remember when we were doing that first topic of propositions, right? Then what we were doing was I give you a statement of ands and ors, and I want to know, is it a tautology, right? A tautology is true under every settings, right? So if I ask, is your and or not circuit a tautology, then I'm asking, it does every setting of true and false satisfy it? And if I'm asking, is it satisfiable? Does there exist one? Right? That's over here. Tautology is over here. Satisfiable is over here. Right? Does that make sense?
Yes, thank you, sir.